Crucial to your understanding of this process is being familiar with representing a given force by a vector. Here's one force, and here's another. But to find the resultant force, we connect them together nose to tail. The resultant force is the most direct path from start to finish. You shouldn't have too much difficulty with this, but as is so often the case in maths, going in the other direction can sometimes take a little more effort. We'll be starting with a resultant force and expressing it as two separate components in perpendicular directions. Like this, for example. You should understand that these two components combine to give exactly the same force as this resultant force, since they start and finish in the same place. The reason we want to do this in the first place is that it's much simpler when we have a large number of forces all going in different directions, if we can express all of them in terms of just two directions. And it's even more advantageous if the two directions you choose are perpendicular, since in simple terms they don't interfere with each other, so you can consider each direction in isolation. So onto an example. In the sorts of questions you're likely to meet, the first step is draw a diagram that represents the given situation. You'll then draw on your forces, including a double-headed arrow showing the direction, or at least what you believe to be the direction, of acceleration. The next step is to choose perpendicular directions in which you resolve all your forces. And your choice of direction will be dictated by the direction of acceleration, since this is the most important direction. And we add to this our perpendicular direction. So finally we arrive at the subject of this video. All forces on your diagram must be resolved into your chosen directions. The normal reaction is already in terms of our chosen directions, so the only force we need to resolve in this diagram is weight. And we're seeking to resolve this resultant force into two components in these directions. The best way to achieve this is to use a ruler that you only allow to run in the perpendicular directions you've chosen. I'll just tidy this up a bit. And don't forget to consider the directions of the forces. Just consider the direction you must travel to get from here to here. So we're going to go this way and this way. Now we've formed a triangle, and because the directions are perpendicular, it's a right angle triangle. Now to use right angle trigonometry, we need to find an angle in this triangle. And it may be that you can just see that this angle here will be 30 degrees. However, if in doubt, just employ basic trigonometry. Here's 90 degrees. Consequently, this angle will be 60 degrees. And since these directions are perpendicular, making 90 degrees, then this angle here must be 30 degrees. So using basic trigonometry, since this is the opposite side, we have 10g sine 30, and since this is the adjacent side, we have 10g cos 30. Having resolved the force, we can remove the original representation of it, and I'll just tidy up the diagram. What about this? We're applying a horizontal force and need to resolve it into these perpendicular directions. Well, the method is no different. Set your ruler so it's only allowed to run in the directions you've chosen. And use it to get from the start to the finish of your resultant force. again, I'll just tidy it up a little bit. And don't forget to consider the direction of the forces. So our resultant force is starting here and finishing here. So to make the same journey, we'll go in this direction and then down. Once again, we have a right-angled triangle due to the fact our chosen directions are perpendicular. And in this case, it's easy to see the corresponding angle is going to be 30 degrees. So our adjacent side will be 20 cos 30, and our opposite side will be 20 sine 30. And I can remove the original unresolved force. And finally, arrange the forces just so the diagrams are tidier. And there we have it.